Our last example is we're only going to set up this problem. It's to help you with MyMathLab. And so in MyMathLab, you're going to see a problem like this. And it says, an open box with a rectangular base is made from a rectangular piece of cardboard, 40 by 35 inches, and on the side by cutting out a square from each corner and turning up the sides. So before we even go to part A, let's just make sure we understand what's happening. I have this flat piece of cardboard here, and I'm going to cut out some squares. And that really bothers me because it kind of looks like those are rectangles, but we're going to cut out some squares here. And then you're going to take this like darker part and you're going to fold it up. You're going to take this darker part and fold it up, fold up, fold up. And now we have a box with an open lid, right? So I kind of made a really janky looking example of this. I'm going to try to move my camera and hope it moves back properly. Okay, but I have this piece of paper here, right? And so what I have done is if I cut out all of these corners, I know it's kind of hard to see, but if I cut out those corners, then you're folding up, right? These corners, these squares are gone. You're folding those up. And then we have now a box, okay, with an open lid or an open top, but we have a box here. Now, you can kind of see that this box is pretty shallow, but it is pretty wide when I cut out these squares. If I cut out bigger squares, then that's going to fold up even higher and so forth. So how we cut these squares does make the area and the volume, or not the area, the volume of this change. So I don't know if that was helpful or not, but kind of hard to show on the camera. Okay. So now that we hopefully maybe kind of understand what this is talking about in the setup, how we're going from a two-dimensional flat piece of cardboard to a 3D object. First thing I need to do is express the volume V of the box as a function of height X of the side of the cutout from each corner. So because we were told somewhere that we have a rectangular base, my volume formula for a rectangular prism is what? Okay, back from our geometry days, you could do base times height or area of the base times the height, but the most basic, easy one would be length times width times height. So what I need to be able to calculate and find from this diagram here is what is the length of this rectangular box, what's the width, and what's the height. Okay, typically length is your longer side, so we're going to start here with this 40. And what I am wanting to know is how I can represent this side right here. And so this is going to come from knowing that the total length is 40. And yeah, that's fine. We'll go L equals 40 is what it starts off with. But then I'm going to be cutting this square out, which is the measurement of X inches. So we'll take out this X and we'll take out this X. Now this is nice because it gives me a formula. It means I can change how big these squares are. If I want to make these squares one by one, I would simply do 40 minus 1 minus 1. That total length would then be 38. If I want to cut out 5-inch squares, then we would do 40 minus 5 minus 5 to get 30. Okay, so this gives us a formula no matter what that square is going to be. And so we can shorthand that. Negative X minus X is 40 minus 2X. So there is my length. Now I need my width. My width is usually the shorter side, but it doesn't have to be. So this is my width right here. What do you think our width would equal? It starts off as 35, and then we're going to subtract that same X. So 35 minus X would be 35 minus 2X. Okay, so again, if I'm cutting out 2 inches here, now I'm doing 35 minus 4, right? If I'm doing 3-inch squares, we'll be doing 36 minus 6, or 35 minus 6. Okay, so it gives me my width. And then lastly, in this formula, we need the height. So if I bring out my janky piece of paper again, what determines right here how tall this is? That's equivalent to how much of the square I'm cutting out, right? Here, if I did an inch, then when I fold this up, this height would be an inch. If I cut out 2-inch squares, then this height right here would be 2 inches. So my height, let me find another color here, is whatever that length of that square is going to be. So here we have h equals x. Okay. So now I have my 3 unknowns here. So my volume is simply, when we substitute in, we're going to use some parentheses. So my length is 40 minus 2x times my width is 35 minus 2x, and then my height is x. Now, if we wanted to, we could FOIL these and distribute in the x. We are going to have a quad or a cubic here, but we're not going to make it any harder than we need to. We need to express the volume as a function. I don't need to multiply that out. That is my volume right there. So then part B wants us to graph our volume formula. So to do that, we're going to go into Desmos, and I'm going to try to get this graph in Desmos here. So I'm going to type my volume formula, and you do need those parentheses there. Okay, so there is my formula, wrote with parentheses and everything. Okay, so why does this not match this right here? Well, you have to look at that viewing window. So this is just kind of a nice helpful hint for you. When you were in MyMathLab and you were trying to get your graph on your computer or even your graphing calculator to match the graphs that you see in Desmos, you need to look at their viewing window and mimic it. Okay, so I'm going to minimize this again so my graph gets a little bit bigger. But we can see from here that my x min is 0. And then my x max is 18. So on my x-axis, I want this to go from 0 to 18. Okay, so I can see one starting point, and I can see the other ending point, but now I need to figure out how tall this goes. Still, look at that graph. My y min is 0. The highest y value I have is 4,000. So I will now change that window as well. So we're going to go from 0 to 4,000. So here is my graph. Okay. Now, that's all I have as far as the notes go, but this is going to ask you some further questions that I do want to talk you through about. Okay. First, we were able to get our formula in part A. We were now able to graph and get this graph to very closely match this one. You should be using this on like more of a full screen, so that matches a lot better, right? I'm using half a screen, so it does look taller, but it's not. Okay, so let's kind of talk about what these axes represent. What does my x-axis here represent in the context of the problem? It tells me up here is a function of the length x of the side of the square cut out from each corner. So we have a length x of the side of the square cut out from each corner. So this x-axis down here represents my square cutout. I can't write right now. It's a struggle. Okay, square, that's that word square. Square cut out. Okay, and my unit is in inches. Okay, so we can see from this one here, 3, 6, 9, 12, 15, and 18. And actually, I want to show you that as well. When you're in here, that's what this step right here is representing. So this is counting by 3. So if I make this by 3, you get 3s here. This one here is counting by 500. So if I change my Y step to 500, that gets those numbers there to match. And I actually really don't like these little grid lines in here. I think it makes it look busy. So I'm going to unclick my minor grid lines. And so that cleans it up quite a bit. And just so we can see it a little better, I'm also going to change this to big font, but you don't have to do that. Okay. So that makes that match a lot better, but that's what this is showing right here. So we can see if we cut out squares that are 3 inches, 6 inches, 9, 12, 15, and it can't go to 18 because that's not going to work. Okay, so then what does my Y represent? Well, we have set this to equal V. So this is my volume. So this Y-axis is giving me my volume of box. And volume is always in whatever your unit is cubed. So this is in inches cubed. Okay. So for an example, it might ask you something like, what is the volume if you cut out squares that are 1.5 inches? So we can go in here. Okay. And because we're cutting out squares that are 1.5 inches, we're talking about that x-axis. I'm going to come in here, I'm going to put x equals 1.5. And I'm looking for that intersection right here. So this point, when it's at 1.5, is 1.5, comma, 1,776. So if I cut out squares that are 1.5 inches, this is how much volume that box can hold. So you can do that for any number. If it wants to know what's the volume going to be if you cut out 12-inch squares, that's going to be x equals 12 because we're cutting out 12-inch squares. That's what my x-axis is representing. And so that would then have a volume of 2,112. It can also ask you, what is the maximum amount of volume that it can hold? So that should be a key word right there, flashing. What is the maximum amount? It is simply talking about this highest point on this graph, right? So here is my highest point. This is the maximum number or the maximum volume of whatever liquid we have that this can hold. So here is my max. And notice it looks like it's at 6, but this says it's at 6.2, right? So it's just slightly off of that. But this right here is my max. And so in this problem, we had a max of roughly, I'm going to just call that 6.2, comma, 3,867. I guess we'll go with a 0.3. So if we cut out squares that are roughly 6.2 inches, then we'll have our max volume of roughly 3,867 inches cubed right there. So part A and B you will do, so we have done that. You're going to either type in x equals or find the max to find that volume that it can hold. So hopefully that helps you with this homework problem.